In this video, we're going to introduce how you can start to evaluate your model. For this first example, because we're just using the constant model, we're just going to visually compare the two different models that we had using our different loss functions. But in the future, as we do more complicated models, we'll see that there's some basic performance metrics that we'll suggest that you use during this evaluation process. Visually, we can see the difference between what we came up with. One of the cases we said 25, the other case we said 22. What are some pros and cons here? All right, in the mean squared error column, this function is what we call smooth, meaning it doesn't have these little jagged corners like our piecewise one. And in particular, meaning I can use calculus and easily optimize it, finding the minimum pretty quickly. This piecewise has these little kinks, meaning it's not differentiable. It's harder to minimize. We did it. We just did some hand waving about some of the minimization things that come up. But in practice, I think historically we could argue mean squared error ended up being used much more frequently than mean absolute error, mainly because of this minimization. It was easier to minimize using theoretical methods. Now we can do either using numerical methods, but I'd say historically this kind of won out, mainly because of this advantage. Let's compare their sensitivity to outliers. So suppose I were to take this data set and add one more outlier. Let's look now at the difference in my model. So I can see that I have a very slight difference if I use mean absolute error. It went from 22 to 25. But I have a huge difference if I'm using mean squared error. So this is very sensitive to outliers because they're going to change the mean substantially. And this will also vary depending on our data set size. So here I didn't have that many data set points, which is why adding one really big one made a huge difference. The mean absolute loss is much more robust to outliers, which could be an advantage depending on what your data set looks like. Let's also compare my uniqueness of solutions. So something that we didn't address in our original data set of 5 is what happens if you have an even number of data points. How does this mean absolute error solution fall out, or what happens to it? Mean squared error has the property that I will get a unique solution. In this case, with my mean absolute error, if I add a data point here, there's technically infinitely many solutions. Any constant that I want to choose between 22 and 29, because I basically need to split it in half and I need half the data points to lie below and half to lie above. So technically I could pick anything between 22 and 29 and it would satisfy that requirement mathematically. In practice, we have a convention to help us around that where we'll set the median to the average of those two middle points. So in our case, we would have set it to 25.5. But this is just something to point out that is a pro versus con depending on what you're trying to do with your model. Okay, so in summary, we realize the benefits of mean squared error. It's easy to minimize using theoretical and numerical methods. That's contrasted to mean absolute error. It's harder to minimize. Mean squared error, however, is very sensitive to outliers. Mean absolute error is not as sensitive. It's much more robust. So it isn't obvious that one is better than the other. In practice, you get to make that decision as the data scientist, depending on what your data set looks like and what you're using your model for. All right, let me summarize. Finally, let's summarize what we've done with this analysis of the constant model. So in this whole first session, we've been looking at just the constant model. In the coming lectures, we're going to look at more sophisticated models than that. We talked about two different types of loss functions. the L2 or squared loss, and the L1 or absolute loss. There also exist others. These will be the primary two we look at in this class for quantitative data. As we pointed out, there are benefits and drawbacks to both, and so ultimately you get to choose which loss function you want to use for your modeling task. We then solve for the optimal parameters by minimizing the average loss, and we can see we'll get different optimal parameters for different loss functions. That whole process is called fitting the model to the data. And in these examples, we were able to do it by hand using calculus, but we'll see for future models that it will become trickier to do that, and we'll use numerical approximation techniques. And then because we had a simple model today, we visually evaluated our model performance. But in general, for more sophisticated models, there's going to be some common performance metrics that we'll see in future lessons. So where are we headed next? We're going to look at changing the model. And so I mentioned we'll be introducing the simple linear regression model, followed by multiple regression, and then logistic regression. We'll look at changing the loss function. Now, I will give the caveat that the L2 loss will appear a lot, particularly when we're looking at simple linear regression and multiple regression. But we will introduce a new loss function when we get to logistic regression. And then we'll look at how we fit the model to the data. So we did it by hand using calculus for these first examples, but we will look at combinations of models where we're going to require more advanced numerical approximation techniques. I know there was a lot of new vocab and a lot of new notation in this first lesson, so I'm just going to do a quick recap of the key terms that you'll continue to see as we move forward in modeling. First, we talked about our L2 loss and our mean squared error. So squared loss and mean squared error are not exactly the same thing. One is for the single observation, and the other one is your average across the entire data set. So they're closely related. Similar relationship holds true between your absolute or your L1 loss and your mean absolute error. We connected loss functions with some summary statistics we've already been using in this class. In particular, we showed the sample mean is the value of theta that minimizes the mean squared error in our constant model. And the sample median is the value of our constant that minimizes the mean absolute error. One other term or combination of terms you'll frequently hear is not just average loss, but sometimes we'll call it empirical risk. For our purposes, those mean the same thing. And finally, I'm going to show you an overview of common notation that we're using in this class, just as a reminder. Let me just see here. Right, our empirical risk could be the mean of any loss function across our data set. Finally, I'm going to show you some notation review based on what we learned today. So typically we're just going to use Y to represent our dependent or our output, our true observations. Y hat is representing our predicted observations from our particular model. Theta is representing the parameters of our model. We get to choose what we want our model to look like, but theta are the values we're trying to estimate. Theta hat represents the fitted or optimal parameters that we solve for once we have chosen our loss function and we minimize the loss. We will be dealing and using this notation going forward, so feel free to revisit this as needed as you get used to all of these new terms.